what we're going to get into for the rest of the class, except for our last section, which is 7.8, which is kind of standalone, but I like 7.8, is we're going to talk about more exponentials, and we're going to talk about logs. And you may have seen, like your calculator has the button log, or you've heard the word logarithm. Logs are just another way to write exponents. So whenever you see the word log, think, okay, that's related to an exponent. My high school students in the high school I worked with today, they wore little stickers that said a log is just an exponent and had a little picture of a log on it, and they get like an extra point on their quiz if they wore that around all day. So logs are just exponents. And they were originally, I also had to, from one of my classes, look up the history of logs. They were also originally just to make life easier. Like we don't learn in this class kind of some of their neater properties, which are how you can take a long problem and just kind of squish it into one. But back way ago, when they didn't have any sort of calculators, they used to use logs to make calculations very quick and easy. And they would have just books of tables of log values, like millions of log value tables. And people spent like 20 years calculating these things. It was crazy, but it was all meant to save time. So you say, well, why do we do it today? We have calculators. Well, like your computer is still using logs because they save a lot of time on calculations. Okay, we don't get into any of the cool stuff, but we'll get the basics. And then if you go to 135, I know at least has more on that. All right, so let's talk about what this looks like. So there's two forms of these equations that we're going to work with. We have our logarithmic form, and it's equivalent to an exponential form because logs are just another way of writing exponents. They're completely related to exponents. So here is your logarithmic form. Y equals a log base b of x, and that's equivalent to the exponential form is this b to the y equals x. So what we're going to do mostly today is just go between those two forms. You're going to get one in log form, write it in exponential, get one in exponential, write it in log form. And that's going to help us solve problems and evaluate logs that our calculator can't handle. And here's another little known fact, commonly known fact. If no base is written on the logarithm, it's implied to be base 10. So a lot of times you'll see we have the little number here that tells us what base we want our log. If it just says the word log and there's no little number there, it's 10. The base there is 10. I think that's one of your extra credit questions. So if there's no base written, it's implied to be 10. We also have what's called a natural log. And natural logs, so if you see ln, that stands for natural log. It is a log base e. Now, it's not, I always chuckle when I see this. People write, I guess, log. When you write your bases, they're little, and they're a subscript. So you don't want to put it kind of all in line. When we write a log, we write the base as a subscript. So e is just a number. It's kind of like pi. You've got a button on your calculator for e. It's approximately this 2.718, and it comes from, as you find the sum of this thing and it ends getting larger, you get your e value. But think of e, whenever you see e in this class, think of it like pi. Like you've seen pi when you're dealing with circles and things. E is just an irrational number. It's got a set value, as set as we can get, being irrational, and we're going to just use a button on our calculator for that. So we'll talk about using your calculator if you have a problem that has e in it. But it's another extra credit question. Natural log is a log base e. So there it is. Logarithmic function whose base is e is called the natural logarithmic function. So the first thing we're going to do is write each equation in its equivalent exponential form. So notice all of these equations have logs in them. We want to write them without a log. So it's just a quick little pattern to switch it up. So when you look at the two different forms, you can memorize where all the different variables are. But if you remember one thing, it's really easy. The base of your log, which is the little number, is the base of your exponential. So the base is the base in both forms. So the base of this is it's a log base 7. So we're going to start with 7. So the little number we start with is the base of our exponential. To get the exponent, we just go to the other side. So the exponent on that is 2. And then it equals the only number we haven't used yet, 49. And the nice thing is, if these are all numbers, they better be true when you write them. If it's not a true equation, then you got the order wrong, right? Doesn't 7 squared equal 49? Yeah. And again, we're not solving anything. We're just writing it in a different form. Going back and forth between these forms is going to help us in some of our later problems. So on the next, on B, we have a log base 8 of 1/8 equals -1. So you start with your base. What's my base in this one? 8. So we're going to start at the base. That's the base of our exponential. Then you go to the other side. That's your exponent. So we have 8 to the negative first. And then equals the one number that's left over. It's 1/8. Now let's think about if that's true. How do I make negative exponents positive? Do that 1 over. So yeah, that works. 8 to the negative first. It's 1/8. So that's just the equivalent exponential form. And this is the way that we use most often, going from your log to your exponential form. All right, so C, what number am I going to start with in C? 3. Start with the base. The base of your log is the base of your exponential. And then what's the exponent? 1/2, other side. And that's equal to square root of 3. Let's think about if that one's true. How do we know that one's true? Yeah, think back to 10.2. Yeah, 3, 1, 2 is the index, which tells us the 1/2 power is the square root. And you don't have to write that out. Your answer is 3 to the 1/2 equals the square root of 3. But this one's going to come up again. The fact that we have those exponents that can make us radicals. That's going to come up again. All right, and D. D's not one that you could actually spot check because it's not all numbers. You just have to remember the order. And a bunch of them on your homework have variables in them to make sure you've got the order right without just guessing the correct equation. So what am I going to start with in D? 6. You start with the base. The base of the log is the base of your exponential. And which number is my exponent? X, so other side. And that equals the number that's left over, 216. And for this, the directions are simply rewrite. We don't need to solve it. But later on, we'll have directions that ask you to solve, but right now it's just going between the two forms. Questions? So if we go from logarithms to exponentials, we've also got to be able to go from exponentials back to logarithms, which I think isn't maybe quite as intuitive, but it follows the same basic pattern. So you want to write each equation in its equivalent logarithmic form. Now, people who aren't here today get the drill on Friday and just see a bunch of true equations. Like, yeah, sure, 9 to the 3rd equals 729. The directions say to rewrite it. So the first thing we want to start with is log. Now we want to find its base. Remember, the base is the same. The base of the exponential is the base of the log. So the base of the exponential, 9. Now when you write your base, let's pretend, let's go back to elementary school. I guess these would be solid, right? Do one of these. All right, so we're going back to you remember when you learned how to write, you had the paper that showed you how high everything should be. Okay, so you write the word log. The base is a subscript. So it shouldn't be as big as the word log, and it shouldn't be in line with the word log. The base is a subscript. So the base is little and it's sunken down a little bit. Now, just like before, the second number we always skip to the other side. Same thing here. Second number, skip to the other side. The pattern's the same. Take your base, go to the other side. There's my 729 equals the only number that's left, 3. So that's a log base 9 of 729 equals 3. Everything should be in line and the same height except for the base, which is a subscript. I know it can sometimes be hard to tell from the overhead. So everything else is in line except for the base. So in B, I have 3 to the 4th equals 81, which is a nice true statement, but we just want to switch its form from exponential to logarithmic. So I'm going to start with the word log. And then which number is my base? 3. So the base of the exponential is the subscript on my log. And then just like before, go to the other side. Give 81 and it equals the only number that's left over. And then C, what's the base of my log? 2. So the base of the exponential is the base of the log. Going over to the other side, that's the number I'm taking the log of, which is 1/8, equals the only number left, -3. And the way I usually check myself on these is after I write them, I think about going backwards. I say, okay, 2 to the -3rd equals 1/8. Because I think that way is easier. So for my check, I actually look at rewriting it as the exponential. And then D, 4 to the y equals 64. And we're not solving it. We just want to rewrite it. So we're going to start with our word log. And what's my base? 4. Other side, 64 equals the only thing that's left, y. I'm going to tell you, it doesn't get a whole lot worse than that for our logs. If you know how to go between the two forms, we're going to use a few more rules of exponentials and evaluate. But there's not too much more to our logs in this class. Questions? So the next thing we want to do with these logs is we want to evaluate them. And you might be like, sweet, I have a log button on my calculator. Unfortunately, your calculator handles logs base 10. And that's it. But this has a base of 2, a base of 3, a base of 25, a base of another base of 2. So it's not going to just go into our calculator. What we're going to do instead is we're going to write this as an equation. Because once I have an equation, I can just flip forms back to the exponential. So I want to set this up as an equation. Well, the way you do that is I say, okay, log base 2 of 8. I don't know its value. What do we use in place of a value we don't know in math? Yeah, x. So I'm going to say this equals some unknown value, because I don't know what it is. But now that I have this set up as an equation, I can switch it to exponential form. So I don't know how to handle logs, but I can handle the equations that don't have the logs in them. So now I'm going to switch its form. So I'm going to take 2, take my base, my exponent is x, and it's equal to the number of left over, just like we did on the front. And now, most of these are going to be just a spot check to see, okay, you're going to have to ask yourself, 2 to what power gives me 8? 2 to what power gives me 8? 3rd. So we know then that x equals 3. Or what we're really finding out is that log base 2 of 8 equals 3. So what you're doing when you're evaluating one of these is, again, you're looking for an exponent. You're looking for what exponent makes my base equal to the number I'm taking the log of. So for B, we have log base 3 of 1/9. We want to find its value. We don't know it, so to make this an equation, I'm going to set it equal to x. And then I can switch formats. So when I go to write my exponential, what's my base? 3. And then I go to the other side. I have it to the x power equals 1/9. So now I need to think 3 to what power gives me 1/9? Well, the first thing to think about, How do we get a fraction? When do we have that 1 over situation? What's true about the exponent? Negative. Good. If you have a fraction, we know our exponent's negative. It's the only way we get a fraction out of that. So because this is a fraction, we know x is negative. And then it's just a matter, so x is some negative number, it's just a matter of saying 3 to what power is 9. So 3 to what power gives me 9? Yeah, it's the second, so I have to have a negative 2 to get that fraction. So you're still just looking at the relationship between the 3 and the 9. We just have a negative number. That's how we get our fraction. Adam.
What's the word after fraction, negative root?
No. I can have better penmanship. If it's a fraction, we know x is negative. Yeah. No, but the reason I do that is I just want to show you that even though it looks like we're just solving an equation, what we're actually doing is evaluating. We're finding the value of this. That's the process that we're doing, is finding the value of that. All right, C, I have a log base 25 of 5. So I don't know its value. I'm going to set it equal to x. And then I'm going to rewrite this. So my base is 25. Go over to the other side, raise to the x equals 5. We haven't had a situation where the number ever got smaller other than a fraction, but fractions just mean there's a negative. So we're going to have to think outside the box a little bit. Who said that? All right, Napoleon. How do we get a square root? So 5 comes from the square root of 25. I think we probably agree on that. What exponent is equivalent to a square root? 1/2. We talked about this back in Unit 3. We brought it up again on the front. The relationship between these two is that 5 comes from the square root of 25, which means that this is going to be a fraction in the exponent. And the only two that you're going to see, you're not going to see some crazy fractions. You might see 1/2, which is a square root. When exponent's 1/3, what kind of a radical is that? If your exponent was 1/3, cube root. And if you had 1/4, it'd be a 4th root. If you had 1/5, it'd be a 5th root. 1/6 would be a 6th root. You're not going to have anything fancier than that. It'll always be square root. Really, it would be square root or cube root. So if you need a square root to get from your left number to your right number, because those are our only options. We can only raise it to powers. We can make it a fraction if we have a negative, or we could take a root. We can never divide. We can never add or subtract. Our only options are multiply it by itself, make it a fraction with a negative, or take a root. So here, x has to equal 1/2. And we'll actually learn on Friday, which is kind of backwards, I think, in your book, another better way to solve that. But for now, if you see that you need to take a square root, it's the 1/2 power. A cube root would be a 1/3 power. So I want you to go ahead and try D, E, and F. On E, there's no base written, and it's a log. What's my base going to be? 10. So you might want to put that in on E. All right, so D, log base 2 of 1/4. So we go ahead and we don't know its value, so that we can rewrite it, we can put it equal to x, and it's got an answer for D. 2 to what power gives me 1/4? -2. How do you know it's a negative? Fraction. For a fraction, all you know is that your answer is negative. Then you look at 2 to what power gives me 4. So that one was pretty good, actually. Most people got that one. All right, the log base 1,000. Again, this is also one of your extra credit questions. If there's no base written, what could I put in there? 10. if it's a log. If it's a natural log, we put in the little letter e. So this is going to be equal to x. So I'm going to take the base I had to add, the x I had to add. So I have 10 to the x equals 1,000. So I saw some tens, I saw some hundreds, and I know what you were thinking. You were thinking like 10 times 100 is 1,000, but we're looking for a power. Tens are actually the easiest. You just count the zeros on your answer. So you say there's 1, 2, 3 zeros, so x has to equal 3. It's that easy every time. You just, for that, the logs base 10 are the easiest, in this class at least. You just count the zeros. Because 10 to the third is 10 times 10 times 10, which that's 10 times 100, which is what a lot of you were trying to go for there. If you're not sure, just put it in your calculator. Again, I think if you put 10 to the 100 in, you'll probably get an error because the number is just too large. So that's 10 times 10 times 10, 100 times. We don't need it quite that many. We only needed 3. And then really happy with how many correct answers I saw in this last one. So I think we've got the pattern. You set it equal to x. You rewrite it. But then, what's the relationship between 27 and 3? How do I get from 27 down to 3? Cube root. I would take the cube root. The cube root of 27. Again, I'm not going to give you like crazy numbers. There'll be things we've seen a lot from Unit 3. What exponent is equivalent to a cube root? 1/3. So the two you really might see are just 1/3 and 1/2 if you want a cube root or a square root. Questions? All right, the last thing we're going to do with logs today is we're going to find the domain. So we find the domain of everything. So let's think of all the, and this is one of the, they put them all together on your final exam review. On your final exam review, number 9 has you find the domain of a rational, which was Unit 2, the domain of a square root, which was Unit 3, the domain of a polynomial, which is Unit 2, the domain of an exponential, which we just did last class, and the domain of a log. So we took the domain of lots of stuff all throughout the course. So logs fall under that rule. So some of them, like exponentials, domains are always the same. Quadratics, domains are always the same. When we had rationals, we had a trouble area. When we had rationals, we had, you cannot have the denominator equal to 0, and that would give us our domain. When we had square roots, what was our trouble area with square roots? Well, what had to be true about the radicand? Couldn't be negative. So we'd say, we take the radicand, we set it greater than or equal to 0. So just thinking back, because we got a lot of stuff we got to start pulling back up. So this is going to be similar to our trouble area problems, not our just negative infinity, positive infinity. So there's a trouble area for logs. And that's whatever you're taking the log of has to be greater than 0. So if you actually look back, it should be on the front. You see right here? It's a little thing that you probably cursed right over, that x has to be greater than 0. So whatever we're taking the log of has to be greater than 0. So what I'm going to do in these problems when I'm asked for the domain, whatever I'm taking the log of cannot be negative, it cannot be 0. It has to be greater than 0. So all you do is you take the piece you're taking the log of, dump off everything else. All I'm concerned with is that x plus 6 has to be greater than 0. The base does not affect it. Base has no bearing on my domain. It's just whatever I'm taking the log of has to be greater than 0. And I want to solve it. So solve that. I'm going to subtract 6 from both sides. So I know x has to be greater than negative 6. But let's read those directions. How do I need to write my answer? Interval notation. So we need to set up an interval that shows x greater than negative 6. So if I think on my number line, it goes from negative infinity to positive infinity. Which side of that number line has numbers greater than negative 6? The right side, okay, so we know we're over here. Am I including negative 6 or no? No, because I don't have the equal to. It's just greater than. So square roots we had greater than or equal to, so zeros were okay. In logs, even 0 is not okay. It has to be positive. It can't even be 0. It just has to be positive. So how do I show that my interval doesn't include negative 6? What's parentheses? Parentheses or don't include. So my interval is going to be negative 6 up to infinity. That's my domain in interval notation. So for B, when you think about logs, what you're taking the log of has to be positive. Can't even be 0. Has to be positive. So whatever I'm taking the log of, which is 5 minus x, has to be positive. This is by far the most missed drill question on the 12.2 drill, is find the domain. Set what you're taking the log of greater than 0 and solve. So I'm going to subtract my 5. So I have negative x is greater than negative 5. And how do I finish solving for x? Divide by the negative, negative 1. But what happens to my inequality when I divide it by a negative? Change it. So it's x is less than 5. So we divided by negative. We had to flip. Sorry, let's go back. Let's get our visual for our interval. So which side of the number line has our values less than 5? The left side this time, because we're less than. Am I including 5? No. So it's going to be a parenthesis again. Where does this interval start for my domain? Where does this one start? Negative infinity. So since we're all the way to the left this time, we're going to start at negative infinity and go up to 5, but we're not including it. Parentheses.